In this section, we're going to review inverses just a little bit and spend a little bit more time talking about radical functions. So back in 3.7, we learned about inverse functions. And as a review, for a function to have an inverse, it must be 1-to-1. Remember, for it to be a function, let me just draw this picture. For it to be a function, it has to pass the vertical line test, right? Well, if it is a function and it passes the horizontal line test, then it has an inverse. If it passes the horizontal line test, that is what makes it 1-to-1. Okay? To find an inverse function, this is what we did back in chapter 3. You switch x and y and then solve for y. There were a few more steps involved in all of this, but that's the main gist of it. To verify that two functions f and g are inverses, you must prove that f of g of x is equal to x and g of f of x is equal to x. So it's a proof, and you have to show that both of those are true. The graphs of functions and their inverses are reflections over the line y equals x. So if you have your coordinate plane, remember y equals x is this line. This is the line y equals x. So let's say that our function is, I don't know, this one. Well, if that is our function, its inverse will be reflected across this line. So it would look something like that. That's what it means for a function and its inverse to be reflections across the line y equals x. So let's look at this first example. Show that f of x equals 1 over x plus 1 and g of x equals 1 over x minus 1 are inverses. And they put this condition in there that says x is not equal to -1 or 0. Remember, your denominator can't be 0, so it can't be -1 here, and it can't be 0 here. So they had to tell us this just in case for some reason we found out that x were one of those values. Then it wouldn't even work. Alright, so to make this proof, we have to show that f of g of x equals x, and we have to show that g of f of x equals x. Okay, we have to prove those two things. So let's do f of g of x. That means to put the function g, this one, inside the function f. Well, that would become 1 over something plus 1, right? That something is our function g, so we put g in there. 1 over x minus 1 is the function g. Okay, let's simplify this. We don't really need these parentheses because it's just this minus this plus this. So if we combine our like terms, -1 plus 1 is 0, and we get 1 over x. Now we're dividing fractions, and I think a lot of you know the keep, change, flip saying. So we keep the first, change to multiplication, and flip the second. Well, isn't that the same thing as 1 times x? Which is x? Well, that's a good thing. Well, once that one is equal to x, we have to do the same thing for the other one. This time we put f inside g. So we take all of this and we put it in for x over here. So we have 1 over something minus 1. And that something is f. And f is 1 over x plus 1. Now we have to simplify this one. So we have this big fraction again. We're going to keep, change, flip. So we have 1 times x plus 1 over 1 and then minus 1. All I did was keep, change, flip this part to get this part right here. Okay, so we have 1 times all that, which is just all that. So we have x plus 1 over 1, which is just x plus 1. +1, -1, that's 0. So again, we just get x. So to finish out our proof, we say because f of g of x is x, and g of f of x is x. F and g are inverses. And we have finished our proof.